Welcome back to Carneades.org. Today we're going to be continuing with our series, 6 months of set theory and higher order logic. This is month number 2, looking at operations and relations of sets. In this video, we're taking a look at the Union Axiom, Axiom A5. Now, as we learned in the first month of set theory, there are 6 axioms that define a quote-unquote basic universe, at least in the version of set theory that we're looking at. You can formulate the axioms a little bit differently depending on the version of set theory you're looking at, but in our version, we're talking about these 6 axioms. A basic universe is a class that we represent with the letter V. All and only classes are by definition subclasses of V, and all and only sets are members of V. These 6 axioms define what kinds of things are members of V and therefore sets. Last month, we looked at the first 4 axioms of a basic universe. In this video, we're going to cover the 5th axiom, the Union Axiom. So far we have axioms stating that V is transitive, all sets are classes. V is swelled, all subsets are sets of sets are sets. The null set is a member of V, the universe has at least one member. And that any pair of sets is a set, implying the universe is infinite. The 4th axiom, the pairing axiom, allowed us to build sets up from other sets. So to kind of put sets together like building blocks, and therefore prove in the last video of last month that the universe can be infinite because we can keep building bigger and bigger sets. The 5th axiom allows us to break down those sets, to take a big set and turn it into a smaller set in a way of breaking down some of the internal curly brackets, as we saw with unions, using the union operator. So, let's see. The union axiom claims that all absolute unions of sets are also sets. In other words, the elements of any set form a set themselves. If X is a set, so is the union of X. Along with A4, the pairing axiom, this means that the union between any 2 sets is also a set. This is because the pair of any 2 sets is a set, and the absolute union of that pair is a set. And the absolute union of that pair of sets is the same thing as the union between those sets. So, take for example, the union of X and Y. If X and Y are sets by the pairing axiom, so is Z. Z is a set where we define Z as the set of X and Y. By the union axiom, the union of Z is a set. And by our definition of absolute unions, the union of Z is identical to the union of X and Y. The formal definition of the union axiom that we will use is for all X, X is a member of V implies that the union of X is a member of V. We'll call this Axiom 5 or A5 in proofs. Next up, we're going to take a look at a couple of big, long proofs that we are going to try. The first one is the intersection theorem. We don't need an intersection axiom because we have the union axiom and it can do a lot of work for us. But first, give these a try and subscribe and hit that notification bell so that you can be aware when the answers are up and about and when our next video is out. So first off, we have some class definitions, and we'll look at the answers to the last video's exercises. So yesterday's answers include the intersection of A is simply the null set because there are no members shared by all of B, C, and D. The intersection of D is the set of the null set because both E and F, the 2 members of D, have the null set as a member. The intersection of F is the null set because nothing can share members with the null set, and so the null set doesn't have B, C, or D in it, so the intersection of F is just the null set. And similarly with the intersection of E being the null set because no members are shared by the null set in any other sets. However, here's a bonus for you. What's the intersection of the intersection of E? Why, it's the universe. The whole universal class is the intersection of E, which is one of the reasons that we can't say that all intersections of sets are themselves sets. The reason for this has to do with it basically being vacuously true, but we'll take a look at that not in the next video, but in the one after that, and prove that the intersection of the null set is equal to the universe. But for now, try this proof, and we'll go through the whole proof of it in the next video. This is the intersection theorem, that for all x, if x is a member of the universe, so x is a set, and x is not equal to the null set, then the intersection of x is a member of the universe, or the intersection of x is a set. So in other words, for all sets, the intersection of those sets is a set itself, unless that set is the null set. So give that a try, give that a shot if you have the logical chops to go through it. But otherwise, we will take a look at a step-by-step proof of that in the next video. Watch this video and more here at Carneades.org. Stay tuned for a new video every single day for the whole of October. And stay skeptical, everybody.